Hello everyone, my name is Paige. I would like to present you the paper entitled The Scenario-Based Analysis of a Deep Learning Occupancy and Window Recognition Approach for Energy Efficiency. I am currently a PhD researcher at the University of Nottingham, and this shows an outline of the areas which will be covered in today's presentation. The motivation for this project is from the significant amounts of energy used by buildings, which results in today's consequences. With HVAC systems being the main parts required to keep a building functioning, therefore it is important to develop energy-efficient techniques to minimize losses associated with building systems, enhance performances, as well as improve building indoor air quality and conditions. Control systems are implemented into buildings to provide a solution to minimize building energy consumption. Through the use of building energy management systems, current HVAC systems are based on the operations of static profiles. However, with occupancy rapidly changing due to their flexible work hours, current static controllers cannot cope with this. Evidence is presented in terms of the building energy and its performance gap. To understand occupants' movement within buildings, sensors allow accurate detection. Traditional sensors such as these provide both benefits and limitations. Camera has limitations in terms of privacy, but can be overcome through the concepts of AI and deep learning. This shows some existing research in use of vision-based deep learning techniques that forms framework using optical cameras to enable occupancy detection and recognition. Detecting occupancy activities can aid building HVAC systems operations solely based on the greater knowledge and monitoring of occupancy gains. However, there are many other occupancy behaviour which also affects building operations. With the rise of COVID situation, occupancy action towards the opening and closing of windows is important. Manually window opening is one of the most common natural ventilation strategy which is employed within most buildings and especially within the UK. However, due to occupancy actions, window can be easily left open and or remain closed, which leads to an increase in building energy, poor ventilation and poor indoor air quality. Existing window detection-based solutions were intended to cope with future developments through sensors that are connected to building energy management systems. However, given by these solutions developed by these two companies, limitations occur within its design. This includes the requirement of sensors to be installed on every single window, or that it requires existing building windows to be replaced with automated windows. Therefore, this shows that the need for development of a solution to effectively manage building energy performances through minimization of building energy loads, improve system operations towards the provision of better indoor conditions in terms of thermal comfort and also indoor air quality. So currently, there is no application that consists of the combination of deep learning with occupancy activity and window recognition for building HVAC controls and energy management. The aim is to develop a vision-based deep learning framework that enables real-time detection of the occupancy behavior within a building space that could provide data for building control systems with real-time responses depending on the actual space requirements. This is designed to effectively reduce unnecessary building energy loads and improve the indoor thermal conditions. To develop such approach, the following objectives were made and will be discussed within the next following slides. The following section presents the methodology. This is an overview of the framework approach where the deep learning model for occupancy and window detection was developed and applied. Deep learning profiles performed from the live detection of windows and occupancy provide data to be given to inform system controls. For this present study, the following method was applied. A case study building was used to assist two parts of the method, where step 1 consists of the development of the vision-based detector with its application within a real-time experimental test, while step 2 consists of the framework performance analysis based on the detection performance, along with the assessment using building energy simulation for the determination of the effectiveness of the system controls. To form the vision-based deep learning detector, these are some of the images which were collected and labelled as the selected response outcome. It formed the initial part of the deep learning model process, where TensorFlow was used to train a deep learning CNN-based model to perform real-time detection. Part 1 consists of the data analysis and the development of the deep learning model, while Part 2 consists of utilizing the trained model to provide live detection and recognition. A CNN image-based neural network was selected to train the deep learning model. This shows the architecture of the developed CNN. The network is based on the transfer learning approach using the TensorFlow Object Detection API and also the pre-trained model of the faster RTN with Inception v2 model. A lecture room within the University of Nottingham was used as the initial test room and was also modelled as the case study building for building energy performance analysis. This shows the building floor plan and the detection setup for the experimental test. To avoid privacy issues, data from the real-time camera detection of the recognized occupancy and windows were processed and recorded in form of the deep learning influence profile. For occupancy activities, the detected activity corresponded to the gains which were given by CIBC Guide A, Table 6.3, as shown here. To assess the deep learning-based approach, scenario-based cases were used to set up for building energy simulation to investigate the approach towards building energy and thermal performances. The scenarios consisted of the following setup within the selected case study building, with the assumption of full capacity of occupants in the lecture on day 1 and half capacity in day 4. For the rest of the days, the room was assumed to be empty. This was a 4-day scenario where only 2 lectures were occurred. Based on this proposed framework, 5 simulation cases were developed. Case A consists of the different combinations of using constant static profiles for occupancy, window, heating and cooling. For these cases, occupants were either 1. Assumed to be not present in the room and mainly performing sedentary activities during building operational hours, and 3. Present in the room and mainly performing high-intensity activities. Additionally, it was assumed that windows were either constantly opened or closed during these hours. Case B represented the situation where both occupants and windows were detected and recognized using the vision-based approach. The detection of occupancy activities aided the adjustments of the operations of building HVAC systems. The heating set point was set at 21 degrees Celsius, which was only set when occupants were detected in the room. As for windows, the windows were detected as opened at around 3 p.m. on day 1. However, no response-based adjustments were made. Hence, the windows was left open until 10 a.m. on Monday, which was day 4. Case C consisted of a similar situation to Case B, but instead, the building users were informed about the window condition on day 1. For this, the window which was left open after the lecture on day 1, it was detected, and the building manager was informed to close the windows at around 5 p.m, so which was 1 hour after the end of the lecture. In Case D, the building user or manager did not respond to the notification made, and the direct response was made by using the HVAC controls by switching off the heating system when no people or opened windows were detected. While in Case E, the system response was improved further, in addition to adjustments of the HVAC operations and informing building users about window conditions. The approach assessed the number of windows that should be opened would be dependent upon the number of occupants within the room and the indoor room temperature. Next, I will be discussing the results. For the trained detector, an initial evaluation was made using still images located within the test dataset. Here shows some of the detections made. From this, the following confusion metric results and the following evaluation was achieved. It showed an overall accuracy of 92.7% for activities and 87.7% for windows. Along with this, an F1 score of 0.89 and 0.93 was achieved for both responses. Here shows an example of the real-time detection of occupancy and windows during the experimental tests performed within the case study building. The camera allows real-time detection with direct formation of the deep learning influence profile. Accurate detection can be shown here. However, there are still some errors in detection, which shows further developments are required to achieve higher accuracy with better understanding of the true conditions within a building space. Based on the detection on the experimental test for a day in the selected space as shown, here shows the average detection accuracy for all responses. Sitting achieved the highest percentage with 97.67%, while standing and walking achieved a similar result due to its similarities, so confusion might have occurred when distinguishing between the two activities due to similarities in terms of the occupancy actions. Window A achieved a lower detection accuracy compared to other windows, as it may have been influenced by factors such as the window angle and the camera position, and also other environmental factors such as glare. Deep Learning Influence Profile provides the identification of the number of occupants performing each activity and the number of windows within the building space. For this, there was an error of up to 8.2% for occupancy activities and 20.9% for window detection compared to the true occupancy behavior and window condition. This suggests that further improvements is required. However, based on building energy simulation results in terms of occupancy gains, it suggests that if no detection approach was implemented using case A, building operated based on fixed schedule profiles of heating, cooling, occupancy and windows, there would be a significant over and underestimation of the internal heat gains. Based on the ventilation heat losses, it also provides a similar suggestion, whereby inaccurate estimation of up to 170% can be achieved. Hence, this indicates the importance of such approach to recognize whether a room is occupied or unoccupied, and the knowledge of the types of activities performed, and also whether windows are either opened or closed, as this can have significant effect upon the ventilation conditions, air quality, and also the building energy consumption. Comparing Case A, where no approach was made, Case C consists of a response towards informing occupants to close windows when not required, and also Case E, where the HVAC system operation with occupancy response is made. It suggests that the room indoor air quality can be effectively improved. Although a lower ventilation heat loss was achieved for Case C during the lecture period in Day 4, it also led to a very high CO2 concentration, where the occupants did not open the windows. In Case E, both the number of occupants and windows opened which were considered in the decision-making process of the control system. It's assumed that 2 windows were opened during the lecture period as per recommendation by the system. This results in the CO2 concentration to reduce from 2,200 to approximately 1,000. Although the air quality is still poor, it can be further reduced by enabling the system to suggest the room to be more naturally ventilated by having more windows to be opened when required. In conclusion, we have developed an initial demand-driven, deep learning-based framework for the detection and recognition of occupancy activity and window opening behavior within the building space. The real-time based monitoring of the occupancy within the building space using the combined vision-based deep learning approach enables the monitoring of the number of occupants, activities performed by the occupants, the number of windows opened and closed. This led to the prediction of room internal heat gains and the levels of CO2 concentrations. This enables the system to inform occupants to close or open such number of windows and to enable the demand control HVAC system to provide the correct requirements when required. Future work includes the developing of a streamlined framework-based solution to define the required HVAC control system conditions based on a given real-time detection responses. This includes the most suitable indoor room set point temperature that should be assigned to the HVAC system to provide adequate thermal conditions based on a real-time understanding of the utilization of the space by occupants. Thank you for listening. I hope you have enjoyed the presentation. I am open to any of your questions. Thank you.